Good day, students. Today we are going to review the topic waves, and we are just going to go right into it. Wave is a very common concept in physics, so we are only going to talk about the definitions, the properties, the types, and the mathematical representation of the parameters that we are going to be seeing under wave. What is a wave? And what are the types of waves that we have? A wave generally results from disturbance. There will never be a wave except you decide to disturb a medium. If you have still water in a bowl, the water surface remains still for as long as you leave it there. But the moment you drop a stone onto the surface of water, then waves will be generated, patterns, ripples will be generated on the surface of water. Those ripples represent the waves that you have caused simply by throwing stone on the surface of water. If you speak into air, the air is known to have been disturbed by the sound energy that you have passed into it. So that also amounts to a disturbance. So generally, we say that wave results from disturbance. Disturbances are what creates a wave. So we define wave as a disturbance which travels through a medium, transferring energy from one point of the medium to another without the actual displacement of the medium. I'll go over that again. A wave is a disturbance that travels through a medium, transferring energy from one point to another without the actual displacement of the medium. We are going to look at each of the part of that definition that we so have. We said a wave is a disturbance. There must be something that is going to the medium to disturb the medium that was elsewhere very, very still. So the wave is a disturbance. It travels through a medium. There must be a medium for a wave to travel. There must be a medium for a wave to travel. The medium can either be solid, can be liquid, can be gas, can also be some electromagnetic medium that we are still going to consider later. So a wave is a disturbance. It travels through a medium. For example, if I drop stone inside water, the stone is going to create a disturbance on the surface of water. The water now becomes the medium, and we are going to have ripples on the surface of water that represents the wave on the water. If I speak into air, the air is the medium. The sound energy that I've passed into it is what I've used to disturb the medium. So a wave must always result from a disturbance, and it must travel through a medium. It will transfer kinetic energy from one point to another. When you drop stone from any point, the stone before dropping has a potential energy. We are going to consider that under work energy and power. By the time the stone gets to the surface of water, it turns its kinetic energy. Its kinetic energy will be turned to kinetic. Its potential energy will be turned to kinetic energy. And that kinetic energy will be transferred to the surface of water. The energy will now, the movement of that energy across the surface of water is what you are going to see as the ripples. So what a wave does is to take energy from one point where it has been dissolved, where it has been disturbed, and transfer it to other points in that medium. If I speak into air, of course, my sound energy has been passed into air. What air will now do is to transmit that energy across the length of air from myself, the speaker, to the listener. So what a wave does is to transfer energy from the point of the source to every other point that the medium stretched to. So a wave is a disturbance. It travels through a medium. It transfers energy from one point of the medium to another, but it does not cause the actual displacement. It does not cause a permanent displacement of the medium. What does that mean? If, for example, we have water in a bowl and we drop a tiny sheet of paper at any point on the surface of water, we just place that sheet of paper at any point on the surface of water, and we decide to drop a stone onto the surface of water. It is the stone that is coming to create the disturbance, and we will start to see ripples that is emanating from the point where the stone will get to the surface of water. Those ripples will spread outward from the point where the water has been disturbed, because we said that wave involves the transfer of energy from one point to another. As those ripples passes the sheet of paper that you have dropped, you will see the sheet of paper dangling up and down, showing that it is experiencing some form of movement by the movement of the ripples or the waves across the surface of water. But of course, a wave will not be propagated forever. It will eventually have to stop and the water will remain in still posture. The moment the water becomes still, you will discover that the sheet of paper will remain exactly at the point where you have dropped it. Meaning that while the wave was passing through the sheet of paper, it was creating some form of movement that was being experienced by the sheet of paper. You think the sheet of paper was actually moving. But when the wave is over, you find out that the sheet of paper remains exactly where it is. That means the wave has not caused any permanent displacement. It has displaced the sheet of paper, but that displacement is not permanent. It left the sheet of paper where it exactly met it. So a wave does not cause any permanent displacement of the medium. And that is true for every other point on this wave. While the wave is passing through, you will see those points moving to show that something is happening to them. But when that is over, they all go back to the same position where they were. So showing that a wave does not cause while a wave will displace the particles of the medium, the displacement will not be permanent. It will soon return them once it's over back to the same point where they were before the wave was propagated across them. So we say that a wave does not cause any permanent displacement of the medium. So now we'll bring the definitions together. A wave is a disturbance that travels through a medium, transferring energy from one point to another, but it does not without causing any permanent displacement of the medium. There are so many types of waves, and there are so many examples of wave. I just talked about the wave that is generated on water. I talked about the sound wave. I talked about the wave that can be generated or propagated on a rope. If you have a rope and you tie one end rigidly fixed to the wall, then you decide to agitate this other end by just waving it up, you will discover that waves pattern will be generated on that rope, and that is also a wave. If you have a spring and that spring is attached to the end of the spring is attached to the wall, and you decide to move the spring in and out, if you decide to move the spring in and out, the pattern you are going to generate on that spring will also be a wave. There are two different waves that can be generated on the spring depending on how you choose to vibrate it. If you decide to move it in and out, you will see a particular pattern. We are still going to come to that when we get to the type of waves. When you decide to agitate it vertically, the same thing that you did with this rope, you are also going to have another pattern of wave that is traveling across the spring. So wave on water, wave on a rope, wave on string, sound wave are all examples of wave. There are even more common examples. For example, light is regarded as a form of wave too. Only that light is not like every other one. We are going to see that when we start to classify wave. So there are so many examples of wave. Light, infrared radiations, X-rays, gamma rays are all examples of wave. Now, how do we classify waves into the various types that it has? There are three different ways by which we can classify waves. The easiest of them all is classifying waves based on the requirement of a material medium. From our definition, we have learned that wave must travel through a medium. But I was saying it earlier that the medium that is required for a wave may not always be material. There are waves that require material medium before they travel. When we say material, we are referring to things that can either be solid, liquid, or gas, matter. For example, water is liquid, so a wave that passes through water requires a material medium. The water itself is a material medium. Sound requires air. Air is a material. The wave on a rope requires material. The rope itself is a material. So waves that require material, there are waves that require material medium, and there are waves that do not require material medium. waves that require material medium are called mechanical waves, while waves that do not require material medium are called electromagnetic wave. So one way by which you can classify wave is with regards to their requirement of a material medium. When they use solid, when they need a solid liquid or gas to travel through, then they are waves that require material medium, and we say they are mechanical wave. When they do not really require material medium, they do not need a solid liquid or gas, or even when those things are placed in their parts, it causes some obstruction to the propagation of the wave. Then those things are called electromagnetic wave. Electromagnetic wave do not require material medium for their propagation, while mechanical wave require material medium for their propagation. Electromagnetic wave are just the total number of electromagnetic wave that we have is 7. We have only 7 electromagnetic wave. The 7 electromagnetic wave, I have an acronym that you can use to remember them, and it is R-MIVOS-G. R-MIVOS-G forms the acronym that you can use to refer to all the 7 electromagnetic waves that we have. The first one is the radio wave. The radio wave that is used for telecommunication is an electromagnetic wave. Microwave, we are all conversant with microwave, is also an electromagnetic wave. Infrared is the radiation or the wave that deals with heat. Infrared is another one. Visible light, this is just light that we can see. Visible light is also a very good example of an electromagnetic wave. U represents ultraviolet ray. Ultraviolet ray is also an electromagnetic wave. X-ray, more commonly used to form the photograph of intestinal tracts and broken bones in the hospital. Gamma ray. So these 7 are the electromagnetic waves that we have. So any other thing that is a wave that is not air must be a mechanical wave. Sound is a mechanical wave. Wave on water is a mechanical wave. Wave on rope is a mechanical wave. Wave on a spring is a mechanical wave, because all of those ones require material medium. As I'm mentioning them, you can know their material, that the material that is required for each of them. For sound, we require air. Sound does not just require air. Sound can also travel through water, can travel through solids like sand and every other thing. So sound requires a material. Waves that require material can never travel inside a vacuum, because vacuum is nothing. So if they are mechanical, then you must give them a medium, a material medium that they are going to travel through. So if you are asked that what type of waves cannot travel through vacuum, it is mechanical wave. Electromagnetic wave do not require material medium. That means they can travel through vacuum. In fact, light that is getting to us from the sun that creates the day has traveled through millions of kilometers of vacuum before getting to the earth. If it requires material medium, that would not have been possible. So electromagnetic wave do not require material medium for their propagation. So if you are asked to classify waves into with reference to their requirement of material medium, this is how to do it. We classify them as mechanical and electromagnetic. We can also classify waves based on the direction of the vibration of the medium. Now that we know that waves require medium, either material medium or non-material medium or electromagnetic medium, the direction in which the medium are vibrating while the wave passes through them can also be used to classify wave. In that form, we also have 2 types of wave. Considering the direction of vibration of the medium, we have what we call transverse wave, and we also have what is called longitudinal wave. Longitudinal wave. Now, transverse waves are waves that move perpendicularly to the vibration of the medium. Transverse waves are waves that move perpendicularly to the vibration of the medium. Longitudinal waves are waves that move parallel or in the same direction with the vibration of the medium. Generally, there are two movements on a wave. Anytime you generate or propagate a wave, there's a particular direction in which the wave is traveling. For example, if I have a rope that is fixed to a wall, if I decide to agitate this end such that I now have a wave, you will discover that the wave will move from my hand straight to the end, that is the wall. So there's a direction in which the wave is moving. So all waves have a direction. If I speak generally, the sound energy from me will go from me, the source, to the listener, the receiver. So wave always have a direction. The vibration of the medium. Now that we know that anytime a wave is being propagated through a medium, the medium too will have to experience some form of vibration. The vibration of the medium also has a direction. For example, if I need to know the vibration of this medium, all I need to know, how are the particles of this medium, how are they moving as each of the wave pulse passes through them. What we'll do is we'll put a tiny sheet of paper. We cannot see the particles of the medium. We cannot see the particles of the medium. What we can use to conceptualize, to understand how the particles of the medium are behaving as the wave passes through them, is dropping a tiny sheet of paper on the medium. If we put a tiny sheet of paper on the medium, it will help us to understand how each of the particles of the wave are faring as the wave is passing through them. And in this case, you will observe that as the wave passes through it, check how the particle, the sheet of paper that you have dropped, will move. You will discover that as the wave passes through it, the paper will not move in the direction of the wave. Instead, the paper will move, will vibrate vertically upward and downward. It will vibrate vertically upward and downward. As each of the wave pulse passes through it or passes through it, the paper that you have dropped here or at any other point will not move in the direction of the wave. Instead, it will vibrate upward and downward at every point. So if we have a type of wave that moves in a direction that is perpendicular to the vibration of the medium, you will see that as the wave is moving from left to right, the particles are vibrating up and down. So clearly, the vertical movement of the particle is perpendicular to the horizontal movement of the wave. If you have a wave that moves in this direction, we will say that the wave is transverse. A transverse wave is a wave that moves such that the direction of the wave is perpendicular to the direction of vibration of the particles of the medium. It is perpendicular means it is making 90 degrees. That is it. So if you have a wave that moves such that it is perpendicular to the vibration of the medium, they will call those type of wave transverse wave. A very good example is what I've shown. The wave that is formed on a rope is a transverse wave. Wave on water is also a transverse wave. You can get to see that when you have water in a bowl, like I said earlier, and you decide to drop a stone to agitate it, to cause the disturbance, the ripples of wave will be generated. When ripples of wave are generated, at any other point from the point of disturbance, you can place a tiny sheet of paper. The motion of the tiny sheet of paper will help you understand if it is moving in the direction of the wave or it is moving in a direction that is perpendicular to the wave. And if you do that, I'm very sure that what you will have will be similar to this. The paper will not move in the direction in which the wave is moving. While the wave will be moving outward from the point of the disturbance, you will discover that the sheet of paper is vibrating up and down, making sure that it is perpendicular. So water wave is another very good example of transverse wave. Water wave, waveform on a rope are very good example of transverse wave. All electromagnetic waves that I've atomized earlier, all the 7 electromagnetic waves that I've given to you earlier, the ones that form the acronym R-G, are all said to be transverse wave. But we cannot show that because the medium that is required for them is not a medium that we can all see, as they are not material medium. They are electromagnetic medium that are a little bit harder to conceptualize. But we are expected to know that all electromagnetic waves are transverse wave. But it is not all transverse waves that are electromagnetic wave. I must also make that clarification. Water wave, for example, is mechanical. It requires a material medium, and it is transverse. It is not electromagnetic. Wave on a rope is not electromagnetic, it is mechanical, and it is also transverse. So while all electromagnetic waves, the 7 electromagnetic waves are transverse, we believe that when they travel, the direction of the travel or propagation of their wave, of those waves, is perpendicular to the direction of vibration of the medium. When a wave travels such that its path is perpendicular to that of the vibration of the medium, then we say they are transverse waves. Longitudinal waves are waves that moves in the same direction. Longitudinal waves are waves that moves in the same direction as the direction of vibration of the medium. When a wave moves in the same direction as the vibration of the medium, then we say that they are longitudinal waves. So longitudinal waves are waves whose path is parallel or in the same direction with the vibration of the medium. It's no longer perpendicular. And there are so many examples. One very big example of longitudinal wave is sound wave. Sound wave is a longitudinal wave. There's a way you can set up a wave along a spring. There's a way you can set up a wave along a spring that will also make it longitudinal. So longitudinal waves, examples of longitudinal wave, sound wave, very good example. Wave on a spring is also a very good example. There are not too many examples on longitudinal waves, but we have so many examples on transverse waves. Know fully well that all transverse, a class of wave, is even also an example of transverse wave. Now, longitudinal wave. How can we conceptualize? How can we try to understand longitudinal wave? We understand that theoretically, air particles, if I am to speak into air, just before that happens, we believe that theoretically, air particles are neatly arranged, equally spaced to each other. Of course, I said theoretically. This is not how air particles are in reality, because we understand from the behavior of gases that gas molecules move haphazardly. They move randomly in no direction. So it is almost not possible for you to have a system where those air particles, which is also a gas, can be neatly arranged. But theoretically, let us say that it is possible for us to get them neatly arranged for the purpose of the generation or propagation of a wave through them. When you now speak into them, when you speak into this, you will discover that there is a realignment of those particles. Those particles will immediately move in a way that I can represent like this. Some of those particles will immediately cluster together, while others will space out further than they were before. Then you have another region that is clustering together, then another region that will space out, then we have another region that will cluster together, and another region that will space out. So the particles of the wave, the particles of the medium carrying the wave, will behave in an elastic form. You suddenly have them clustering together, spacing out, clustering together, spacing out, clustering together, spacing out, until it gets to the other end where it is traveling to. So we believe that this is how longitudinal waves are propagated. Another very good example that you can have that will make you understand this is if you have a spring. Remember I said there's a way you can also set up a wave along a spring that will make you get a longitudinal wave from it. If you have a spring and you decide to compress it and relax it at the same time, if you compress it inward and relax it, if you compress it inward and relax it, you will suddenly discover that certain part of the spring will cluster around while the next part will space out. Certain part will cluster together while the next part will space out. This is very much like this, and that is how longitudinal waves are set up. So you will see that their vibration, while the wave is moving from the speaker to the listener, their vibration is also in that direction. Their vibration is also in that direction. They are compressing and spacing out, compressing and spacing out, compressing and spacing out, till they get to wherever they are going. This can probably be seen when you sit beside a smoker that is trying to puff out smoke and speak at the same time. You will see the smoke being white will give a coloration, a white coloration to the air, so it becomes visible. And when you start to see the person speaking, you will now see a realignment of the smoke particle, usually also in this form. So when we have longitudinal wave, we expect that the vibration of their medium will be in the same direction as the wave itself. So transverse waves are waves that move such that they are perpendicular to, transverse waves are waves that are perpendicular to the direction of vibration of the medium, while longitudinal waves are waves that are parallel to their vibration, the vibration of the medium. A very good example of longitudinal wave, I said it earlier, is sound wave and a wave on a spring. Now, there are things we should study also under this type of waves. Anytime we have transverse wave, let me take that of a rope. If I decided to attach a rope to a wall, and I decide this time to agitate the rope in the vertical direction. I decide to agitate the rope in the vertical direction. Wave will be set up along the rope. What I'm representing here are the segment of the rope as the wave passes through them. Some of the part of the wave will be displaced upward, while some will be displaced downward as the wave pattern passes through them. When this takes place, we'll say that this is a transverse wave. Why is it a transverse wave? Why the medium, the particles of the medium are moving up and down, are vibrating up and down. The wave is moving from left to right or from right to left, depending on the direction in which you have set up your wave. Now, this is a transverse wave. On a transverse wave, 2 points are always very important for us to mention. Those are the points, the maximum points that are displaced upward, the maximum points of maximum upward displacement. The point of maximum upward displacement are called crests. The point of maximum upward. Of course, there are other points that did not get as high as the crest, but the crest, of course, represents the point of maximum upward displacement. And point of maximum upward displacement are called crests. And that is only possible on a transverse wave. Points of maximum downward displacement. Points of maximum downward displacement are called trough. Points of maximum downward displacement are called trough. So when you set up a transverse wave, there are so many crests and troughs for as long as you allow the wave to be propagated. So we always say, as a way to continue the explanation of the transverse wave, we say that transverse waves are propagated as series of crests and troughs. Transverse waves are propagated as series of crests and troughs. So later on, we are also going to be referring to that later. Now, how are longitudinal waves? How are they propagated? Longitudinal waves are propagated as this. Remember that I said the particles of the medium are seen before the propagation of the wave to be neatly arranged, well spaced, or equally spaced from each other. By the time you set up the wave, across these particles, what you will have is that some of those particles will immediately cluster together, while others will space out, further than they were. Some other ones will immediately cluster together, while others will space out, Then you have some that will cluster together, while then you have the space out. So generally, this is how we believe that longitudinal waves are being propagated. If that is the case, then we have two specific regions that we should refer to. Number one are the clustered regions of the wave. The clustered region of the wave. Those regions, I'm going to call them compressional regions. Regions of compression. So these are compressional regions. And we can keep having more depending on the distance through which your wave is traveling. Then we have the spaced out regions. Spaced out regions are called the rarefaction. They are called the rarefactions. The rarefactions, the rarefaction region, the rarefaction. So those are the spaced out region. What we understand is if the pressure between the air molecules before the generation of the wave or the propagation of the wave is normal, then by the time you generate the wave and the wave is being propagated across the medium, these compressional regions will have an higher pressure, For example, if this is air, if this were to be air, in the normal case, before the propagation of the wave, the atmospheric pressure is said to be normal. It's said to be 1. The pressure here is said to be the normal atmospheric pressure. But the moment you have them clustering together, the pressure here is higher. So we'll say that the pressure of air at the compression region is higher than normal, while because the other region now are spaced out and are much relaxed than even while they were in the normal, we'll say that the pressure here are less than normal. While the pressure in the compressional regions are greater than the normal pressure, while the pressure in the rarefactional regions are less than normal. So that is what we can use to describe longitudinal waves. So we'll say that longitudinal waves can be propagated as series of compressions and rarefactions. Transverse wave can be propagated as series of crests and troughs, but longitudinal wave can be propagated as series of compressions and rarefactions. So for now, we'll move to other types of wave. We are still going to come back to this. We have classified waves based on their requirement of material medium into mechanical and electromagnetic. We have also classified waves based on the direction of vibrations of the medium with relation to the direction of travel of the wave. Now we want to classify wave with relation to their pattern. Then we have what is called traveling wave or continuous wave. Then we have what is also called stationary wave or standing wave. Stationary wave are also called standing wave, standing, while traveling wave are also called continuous wave. So we can classify wave as traveling and stationary wave. Now, what are traveling waves? Traveling waves are waves that is generated and is radiated outward, and it moves outward from the source. Almost all waves fall into that category. When you set up a wave on a rope, there's a point at which you are generating it, and from that point, it will leave the point and move to other points on the medium. If you set up a water wave by throwing stone on the surface of water, it will gradually radiate and move out to other points of the medium. So traveling waves are waves that continuously spread out from the point of generation. They are waves that continuously spread out from the point of generation. Waves, any wave that continuously spread out from the point of generation is called a traveling wave. Meanwhile, standing waves are not like that. Standing waves are waves that are produced anytime two waves of equal frequency, amplitude, traveling in opposite direction are superposed. If I have a wave, let us assume that it is a transverse wave. If I have waves set up on a medium, and I have another wave of the same form, let me just refer to it as the same form now. I've not defined frequency and amplitude that we are going to use to properly characterize it. So let us say we have wave of the same form, now moving in opposite direction. A wave of the same form, now moving in opposite direction. Let us assume that it is possible to continuously generate the wave that is moving from left to right, and it is also possible for us to continuously generate the wave that is moving from right to left. And we decide to bring the two of them together. This is the pattern that we are going to have. This wave is called a standing or a stationary wave. So a stationary wave is a wave that is produced, number one, from two waves. Those two waves must have the same frequency and amplitude. We are going to see that later. The same frequency and amplitude means they must be of the same form, but must be traveling in opposite direction. When you bring them together, the wave pattern that you are going to generate is called stationary.
So this is the meaning, this is how a stationary wave looks like. And it is, we can generate it. I'm going to talk about how to generate a stationary wave later on. But let me emphasize how a stationary wave is formed and what you need to form it. I said, number one, there must be two waves. They must be moving in opposite direction. They must have the same frequency and amplitude. They must be of the same form. One must not be bigger than the other. One must not be faster or smaller than the other or slower than the other. When you bring them together, you will have a stationary wave. So a stationary wave is a wave that is obtained when two waves of equal frequency and amplitude traveling in opposite direction are superposed or are combined. So on a stationary wave, we will definitely say that a stationary wave is different from standing. We can only say that a stationary wave involves two standing waves that are moving in opposite direction. If I generate a standing wave in a direction and still on that same medium at the same point, I decide to generate another stationary wave that is traveling in opposite direction, then we are going to have stationary. All waves can have their traveling form if they are just one, and all waves can also have their stationary form if it is possible for us to take two same form of that wave and superpose them at the same point. Anytime we have a stationary wave, there are two basic points that we should also talk about. Those points are points that I call the node or the nodal point and the antinode or the antinodal point. The nodal points are points of zero vibration. They are points of zero vibration. They are points that are permanently they are points that are at rest. I'm going to show you this point is at rest. This point is at rest. It has no displacement. Point of zero displacement, point of zero vibration are the nodal points. Nodal points are points of zero vibration. So these are the node, these are the node, the node, the node, the node, the node, the node, and nodal points. The antinodal points are points of maximum displacement or maximum vibration. They are points that are completely displaced from the rest position. This line in the middle represents the rest position. So points on those lines are nodal points. Points that are farthest away from that line are the antinodal points. So this is an antinode. This is an antinode. This is an antinode, 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 antinode. This is, of course, also an antinode, 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 antinode. Don't confuse the antinode with what I said about transverse wave earlier. Those are crest and trough. And for crest and trough, they occur for only transverse waves. Transverse waves are not stationary waves. They do not take this form. They are just one single wave traveling from one point to another that is perpendicular to the direction of vibration of the medium. So these are the various types of waves that we can have. So if you are asked to classify wave, usually the question will tell you the form in which they want you to classify it. If you are asked to classify waves into the requirement of a material medium, then we can have mechanical wave or electromagnetic wave. Mechanical waves are waves that require material medium for their propagation, while electromagnetic waves are waves that do not require material medium for their propagation. You can also classify waves into transverse and longitudinal. Transverse waves are waves that travels such that they are perpendicular to the vibration of the medium. Longitudinal waves are waves that travel parallel to the vibration of the medium. Then we can also ask you to classify waves based on their form. Waves can be traveling. Traveling waves are waves that spread outward, that continuously spread outward from a source, while stationary waves are waves produced when two waves of equal frequency amplitude traveling in opposite direction are combined. So these are the type of wave. We now look at the terms that we can use to describe a wave. The term that we can use to describe a wave are the following. We can talk about the displacement. We can talk about the phase, points that are in phase. We can talk about amplitude of a wave. We can talk about the frequency. We can talk about the period. We can talk about the wave speed or the wave velocity, either of the two. And we can talk about, probably, I'll just mention this, the displacement of a wave and the time that it takes the wave to cover that displacement. We can also talk about the distance. We don't really need to mention this, but let us see if we can be able to talk about them. Now, if we have a transverse wave, for example, the wave set up on a rope. I always use the example of a wave set up on a rope because that is one very common example. It is something you can actually set up in your various homes and even in classes. All you just need is a rope that is tied to one end of the class and somebody that is at the other end to agitate that free end of the rope. Then you will have a wave that looks like this. That is a wave. It is a transverse wave. Transverse waves are easier to represent. So most of the time, when we talk about the representation of a wave, we just talk about that for transverse and we include longitudinal. We show you how it can also be possible on longitudinal wave. All of this, and a transverse wave can have all of this, and a longitudinal wave will have all of this too. Anytime there's a wave, the wave will have amplitude, frequency, period, and speed. So we are going to try to look at each one of them. Of course, anytime you set up a wave, there's a particular distance that the wave is going to travel. If I set up a wave pulse, there's a distance that the wave is going to travel. It will take the wave some time to travel that distance. If, for example, if I just set up a pulse of a wave, that way I am not vibrating it continuously. I just vibrated it only once, and I allowed the wave pulse to travel from my hand to probably the other end to which I have attached the rope. There's a distance it's going to travel. That distance is going to travel will be the length of the distance from my hand to the wall. There's a time it's going to take it to travel that distance. There's a time it's going to take it to also travel that distance. While it is traveling that distance, I said points of the medium, points of the medium, points of the medium, points of the medium will be vibrating vertically upward and downward. There are points that will be at various parts of the pattern of the wave. There are points that will be on various points on the pattern of the wave. Each of these points will have what is called their displacement. How do we measure their displacement? The displacement of each point is how far that point is from the rest line, from the rest position. How far it is. If, for example, I pick a point for you here, the distance of that point from its rest line is called the displacement. If I pick a point, the distance of that point, how far that point is away from the rest line, is its displacement. If I pick a point at any other point, the distance from it, from the rest position, is also its displacement. So we always represent the displacement with the letter Y. Y will represent the distance with the letter X and the time with letter T. So mathematically, I can plot generally the displacement of a wave, the displacement of the particles of a wave against the distance and the time that it's taking the wave to travel or to be propagated across the length of the medium. When I do that, this is the type of wave that I will get. This is taken to be the graphical representation of a wave. It looks very much like what we have here. This is taken to be the mathematical representation of a wave. This is standard mathematical or graphical representation of a wave. The y-axis must represent the displacement because the displacement is, in this case, vertical. If you are going to measure the displacement of any point, We want to see how far up it is or how far down that point is. Of course, the distance in that case, since we say that this is a transverse wave, and a transverse wave is such that as the particles of the medium are being vibrated vertically, the wave itself is moving horizontally. So I can plot the distance of the wave, the distance covered by the wave. I can plot it on x-axis. The distance is represented as t. So there are two different graphs that we can obtain for a wave. Number one, we can have a graph that has its displacement on y, and distance traveled by the wave on x. So in that case, we'll call that the displacement distance graph of a wave. We can also decide to plot the time travel, the time that is taking each pulse to get to the other end. We can decide to plot it on the x-axis. So in that case, we are having a displacement time graph. What I'm saying in essence is there are two different type of graph that we can use to represent a wave. We can have the displacement distance graph. We can also have the displacement time graph. It is displacement that is always on the y-axis, but x-axis can have the distance or covered by the wave and the time that is taken to cover, that the time that the wave is taken to move from one point to another. So we should not be confused about what we have done. What we are doing is things that concern the particle are put on y-axis because the particles are the ones having displacement, while the wave itself is the one having the distance and the time. The wave is covering distance. The wave is also taking some time to cover that distance. And since the wave is transverse, I'm putting things that concern the wave on the horizontal axis and things that concern the particles on the vertical axis because it is the displacement. So generally, this is how the form of the waves looks like, and that is it. Now, we want to talk about, I'll start to discuss each of these parameters. The very first one that I would like to talk about that is easiest for us to understand is amplitude. The amplitude is the maximum displacement of a wave from the rest position. Is the maximum displacement of the particle of a wave from the rest position. The maximum displacement of the particle of a wave from the rest position is the amplitude. Every single point, like I've said earlier, that you pick on this wave have a displacement. They have a displacement. If I pick a point and I ask you to find the displacement, just trace it to the y-axis and read out the displacement. But you will discover that there's a particular point that seems to have the maximum, the highest displacement. There's a particular point that seems to register the maximum displacement. There's another point that seems to register the maximum displacement. Downward too, we have the maximum displacement, but this time in the reverse, the maximum displacement in the reverse, the maximum displacement in the reverse. The maximum displacement is called, the maximum displacement of the particle of the medium is called the amplitude, and it is shown as this. It is represented usually with either small letter a or capital letter A. I can show it like this, telling you that it is the distance from the rest position. I can also show you this way by just putting A here. In that case, you get to have minus A, because if it is maximally displaced by 2 upward, it will also be maximally displaced by 2 downward. So if I have 2 here, I must have minus 2 here. So if I draw a waveform for you and I ask you to read the amplitude, it's the easiest thing to read. Just go to the farthest point, the point that has the highest displacement. Read out the amplitude, and that is what you are going to have for that problem. So amplitude is the maximum displacement of the particles of the medium from the rest position. That is amplitude. Now, what about the frequency? Frequency is the number of cycles completed by the wave in 1 second. Frequency is the number of cycles completed by the wave in 1 second. The frequency is the number of cycles that the wave is completing in a second. That means if I am to get frequency on the graph, this axis, must be in time. You know, I told you that the horizontal axis can either be represented with time or distance. Now, frequency is time dependent. That is why I'm saying that the frequency is the number of cycles, cycle completed by the wave in 1 second. What is the cycle of a wave? What is the cycle of a wave? The cycle of a wave is one full pattern by which it will have gone through all displacement in all directions. The full pattern is, by the time the wave starts from this point and comes to this point, it has covered all possible displacements. There's no displacement that it has not covered. And it has covered all displacements in all directions. If it continues from this point, what it's going to do is just going to start repeating the pattern that it has before. It's going to start repeating the pattern that it has before. It's going to start repeating the pattern that it has before. So the whole of the pattern from this point to this point, where it has covered all displacements in all directions, is what we refer to as a cycle. Now, how many of these cycles has the wave completed in a period of 1 second? That is what is called the frequency of that wave. And it's so easy to know. If, for example, I decide to draw these 3 cycles and I put 3 seconds here, what I'm indirectly telling you is that the wave has covered 3 cycles in 3 seconds. So that is not the frequency. The frequency is not this number of cycles it will complete in 3 seconds. The frequency is the number of cycles it will complete in 1 second. So a very simple way to get the frequency, therefore, I'm representing the frequency with letter F, is to divide the number of cycles that you are given by the number of seconds that it took to complete that number of cycles. For example, if I'm to apply that here, the frequency must be equal to, what's the number of cycles that I have on the board? I have 3 cycles on the board. The number of cycles is 3. After completing those 3 cycles, what is the time that it took it to do so? 3 seconds. If I divide 3 by 3, I should have 1. 1 per second, or 1 hertz per seconds, or hertz is the unit of frequency. So I'm going to write frequency as F. The unit of that F is hertz or per seconds. Amplitude, don't forget, is represented by A. Its unit is meters, but it can be in smaller units because the amplitude we are generally expecting for some wave is very, very small. So we can use millimeters, we can use centimeters, but amplitude is a length value, so it will take up the unit of length. So frequency is measured in hertz or per seconds, and we can easily see that. There are so many examples that we can be given. But I would like to say one thing or two about a cycle. A cycle is not circle, but it looks very much like it. If this is a circle, it looks very much like a complete circle. What you call circle, the shape in mathematics that you call circle, that has been divided into 2. So if I now decide to displace the 2 such that I put 1 at the end of the other, I will have that pattern. So this is a cycle. It is possible sometimes for us to be given a pattern like this. Then I'll call this half of a cycle. I expect you to know that this is half of a cycle. We can also be given something of this form, a wave that will just go from its rest position to the maximum point. As long as it gets to the maximum point, I expect you to know that that is a quarter of a cycle. So we can be given full cycles. We can also be given fractional cycles. I hope you'll be able to read them when you have the graph. I'm going to show you an example of where such can be used. If I decide to draw this and stop here, and I decide to put 5 seconds, I can ask you to find the frequency for me. The frequency is the number of cycles completed in 1 second. And you can easily get it by dividing the number of given cycles by the time that it took you to cover that cycle. So we must be able to successfully calculate or determine the number of cycles that we have on the board. Here we have a full cycle. So a full cycle ends here. I also have another full cycle that ends here, making 2 cycles. Then the remaining part is half of a cycle. So I think you will know if I tell you that you have 2.5 cycles. So the number of cycles that I have here is 2.5, while the time that I took it to cover, the time is what is put at the end of it. The time that I took it to cover that 2.5 cycle is 5. So if I cut it out, 2.5 here 1, here 2. It means that the frequency must be 1/2, which is 0.5 hertz. What you are saying is it will cover 0.5 cycles every 1 second. Concept of cycle is one that we should get very well, because most of the time when you say that you have problem with waves that is drawn on a graph, these are the things that leads to those problems. We can be given a quarter of a cycle, I can be given something like this. Then you must have your way of knowing the full cycle, of knowing the cycle. If I have a full cycle, you can count from the back, from anywhere that it is easy for you. I can count from here to here. That's a full cycle. This is half of a cycle. And this is not up to half. It looks like 1/4 of a cycle. So I have 1, half, and a quarter. If you add all of that together in fraction, it gives you 1.5 plus a quarter. That is 1/3. So I can say that the frequency must be the number of cycles all over time. If I'm given the time, let me say 7, it means that the number of cycles that I'm going to use here will be 1/3, 1/3 all over 4 divided by 7. And I can easily split that out as 1/3 all over 4 divided by 7, which is the time. That should be 7 all over 4 times 1 all over 7, and that should be 1 all over 4, which is also 0.25 seconds, or hertz. That is the unit of a cycle. Now we can continue with our study of other parameters of a wave. Period. Period is the time that it will take this wave. Period is the time taken by the wave to complete a cycle. Period is the time taken by the wave to complete 1 cycle. What is the time taken by the wave to complete 1 cycle? That is the period of the wave. The period is usually represented with capital letter T, and because it is a time value, it is measured in seconds. There can be smaller units. In fact, in some instances, I've seen questions where the period has been measured with microseconds, milliseconds. I hope you know that milli is times 10 raised to the power minus 3, while micro is times 10 raised to the power minus 6. The time can be so small that they will refer to it that way. But period is the time that it will take the wave, the time taken by the wave to complete 1 cycle. So if I need to know, I can determine period the same way that I have been determining frequency. In fact, we are going to see later that there's a relationship between frequency and period. For example, I have a wave, a graphical representation of a wave, displacement time representation, and this number of cycles has been given, and I have a time here to be maybe 5 seconds. Now, what I'm saying is this wave has completed 1, 2.5 cycles in 5 seconds. Earlier on, we determined the frequency. We said the frequency is the number of cycles it will complete in 1 second, and we're able to get that. But the period is now the time that it will take it to complete a cycle. Generally, period is determined by dividing the time that they give you by the number of cycles that you are given. Meanwhile, I said frequency is number of cycles all over time. time now, the period now, is the time divided by the number of cycles. When you check these two formulas, you will discover that the frequency is the reciprocal or the inverse of the period. And that is one very important formula that I want you to keep, because we are going to need it very well under this topic. So if you know the frequency, you can easily get the period by inverting it. While frequency is 1 all over t, I hope you know that t will also be 1 all over frequency. Period is the inverse of the frequency. Frequency is also the inverse of period. But more specifically, if you want to find period, let us say that it is period that is required, that you have not even determined your frequency. What you need to do is divide the time that is given on the graph by the number of cycles that you have. If I want to do so here, I will take the time, 5 seconds, and I'll divide it by the number of cycles completed by that wave in 5 seconds. The number of cycles completed by the wave in 5 seconds, if you can count in full. This is 1, this is 2, and this is 2.5. So if I divide it by 2.5, I will have 2.5 here, 1, 2.5 here, 2. The answer is 2 seconds. And that is it. I hope you know now how we count the number of cycles with a wave. This is half of a cycle. This is the other half. And this is another half. This is another half. And this is another half. You can count in half. You can count in full cycles. So each of this pattern that looks very much like is not a semicircle, but it looks like a semicircle, is half of a cycle. So when you count the number of, you can count the number of halves that make up that wave, and you still get it. 1, 2, 3, 4, 5. 5 halves is 5 all over 2, and that is 2.5. So period. The period is 2 seconds. If it were to be the frequency that I need, I will have done frequency is equal to the number of cycles divided by time. The number of cycles in this case is 2.5, as we have seen, and the time that it took the wave to cover that 2.5 cycle is 5. If we cancel it, if we divide, we should have 1 all over 2, and 1 all over 2 is 0.5 seconds. You will find out that 0.5 hertz, or per seconds. You will find out that this is the direct inverse of this. If we do 1 all over 2, we will get 0.5. That is why I said that the frequency is always the inverse of the period, and the period is also the inverse of the frequency. Now, we can continue. So we have defined amplitude, we have defined frequency and period. I wish to go to phase. Phase is a word that we can use to refer to two different points on a wave. We can use to refer to two different points on a wave. If we have a point on a wave, that point has two properties. It has a displacement and it is moving in a particular direction. It has a displacement and is moving in a particular direction. The point that has the same displacement and the same direction with it will be said to be in phase with it. If we have a point, that point will have a displacement and it will be moving in a particular direction. Any other point on this wave that has the same displacement with our point and is moving in the same direction with our point is in phase with our point. For example, I can easily say that if this is point A, the displacement of point A is so easy. I told you if you want to get displacement, just trace it to the y-axis, the distance from here to here, which I can easily get here. That is the displacement of that point. If I can read it off, of course it is not the amplitude. It becomes only the amplitude if you are talking about the point that has the maximum displacement. So that is it. Now, the point that is in phase with this point, point A, there are so many other points that can be in phase with it on this graph. The point that is in phase with it will be obtained by number one, the points that will have the same amplitude with it, that will have the same displacement with it, and number two, the points that we have the points that we have that will be moving in the same direction. All the points on the wave are moving in a particular direction. All you just need to do is You can draw the wave. If this is to be the movement of a person, we'll discover that all the points here are moving upward until they get to the maximum height. Then from the maximum height down to this edge, the points here are moving downward, 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 downward. Once they get to the trough, all points from the trough back to the next crest will be moving upward, 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 upward. Once you get to the crest, as you move down to the next trough, all the points here are moving down, down, down. If you get to the trough, all other points are moving up, up. So it's just like a man trying to move down series of valleys and hills. As you are climbing the hill, you are moving upward. As you are descending, you are moving downward. As you are ascending again back to the hill, you are moving upward. As you are descending to the valley, you are moving down. That is how we get the direction of every single point on the wave. If I ask you for the direction of this point, you don't need to be confused about that, since this point is a point that is placed between a crest and a trough. It is definitely downward. If I ask you for this point, since this point is a point that is placed between the trough and the crest, it is moving upward. Of course, I'm assuming now that we are moving from this point of origin. If we were to be moving from this point, you will get the opposite of that. If we were to be moving from this point, it means here you are climbing and here you are descending. So before you pick a direction for each of the points on the wave, you must assume a direction for your wave. Am I considering the wave from this point to this point, or am I considering it from this point to this point? Now we'll go back to the definition of we'll go back to our discussion on phase. If I wish to now find another point that is in phase with point A, if I wish to find another point that is in phase with point A, all I need to do is I will draw out a line to connect all the other points that have the same displacement with A. I'll draw out a line that is parallel to the rest line to get all the other points that are having the same displacement with A. So let me label those points. If this is A, my reference point, this should be B, that is, this is C, this is D, and this is E. So now I can ask you, which of all of these points is in phase? Some other students will just say, they are all in phase since they have the same displacement. No, it's not only displacement that you watch out for when you are determining points that are in phase. You watch out for displacement, and you also watch out for direction. When you check, the direction of our A is downward. The direction of our A is downward. If we leave from this end, all points here are upward, all the points here are downward, because it is a point between a crest and a trough. Now let's check B. As we move from here to here, we'll discover that B, the direction of B is upward. As we move from the crest to the trough, the direction of C is downward. As we move from the trough to the crest, the direction of D is upward. While as we move from E, as we move from this crest to the 0 point, the direction of E is downward. When we check very well, points A to E have different directions. Yes, they all have the same displacement, but they have different directions. So the only set of points that we have the same, that will be in phase with our point A, are points that have two properties, not just one. With A, they must have the same displacement, and they must be moving in the same direction. While A is downward, C is downward, E is downward. A, C, and E are in phase. And I hope you can also see that by extension, B and D are also in phase with each other, but they are not in phase with ACE. So that is how we get points that are in phase. Points that are in phase are points that have the same displacement, and points that have that are moving in the same direction. Now, I must also tell you, the distance, the pattern between any 2 points that are in phase is a cycle. The pattern between any 2 points that are in phase is also a cycle. For example, we have already defined cycle as the number of the complete pattern as a complete pattern that has covered through all displacements and all direction. But now I'm also telling you that if you pick a point and you pick yet another point, two successive points that are in phase with each other, the pattern from this point straight to this other point forms a cycle. It's a cycle. It is a cycle. A to C forms a cycle. C to E also forms a cycle. So that is how, another way by which you can be given a cycle. I can give you 2 points that are in phase. You can start from, there are instances where a graph will not start from, when a graph is starting from the origin, you understand it. When a graph is starting from the maximum point, you understand it. But I can give you a graph that is not starting from the maximum point and it's also not starting from the origin. If that is the case, I can give you a point, a graph that looks like this. I can give you a point like this. And I can ask you to look for the number of cycles. If you are the person that is always watching out for graphs that will start from the origin or that will start from the amplitude, you have a little problem with this. Why? Because it's not starting from either of the two. But luckily, we'll discover that if we draw a line across, we'll see that the graph is starting and ending exactly at 2 points that are in phase to each other. So I can count the number of, I can decide to look for the points that are in phase and count the number of successive points that are in phase to get the number of cycles that have been given. If this point, the next point that is in phase with it is not this, because this one will not be moving in the same direction. This point is moving up, this point is moving down. The next point that is in phase with this is this. The next one that is in phase with this is this. The next one that is in phase with this is this. So when we check all through, we'll discover that we have one cycle, because I told you that the pattern from one point to another point that is in phase with it is a cycle. So this is a cycle 1, this is the next cycle 2, this is the next cycle 3. And that is how we get the number of cycles. So the pattern between two successive points that are in phase, 2 points that are in phase following each other, is a full cycle. One thing that we are also now going to talk about is a wavelength. The reason why I did not list wavelength is because it is the only one that we are not going to get on a displacement time graph. We'll get it on a displacement distance graph. If you are going to get wavelength, we must get it on a displacement against distance graph. A displacement against distance graph. Wavelength is the distance covered by the wave in a cycle. When the wave goes through a cycle, what is the distance covered by the wave? When the wave goes through a cycle, what is the distance covered by the wave? That is the wavelength. After a full cycle, what distance has been covered? What is the distance that has been covered? That is why this axis must be a distance axis if you are going to get the wavelength. If this axis is a time axis, you cannot get the wavelength. If it is a time axis, you can get the period, you can get the frequency, but you cannot get the wavelength. For you to get the wavelength, you must have a distance, and wavelength is the distance traveled by the wave in one cycle. How do we do that? Very, very simple and easy. We'll just do the wavelength is represented with the Greek letter lambda. This lambda. We'll divide the distance that we are given by the number of cycles that it took it to cover that distance. We will observe that the way we get the wavelength is exactly the way we will get the period if this were to be a time axis. Because the period is the time divided by the number of cycles. So the wavelength is the distance divided by the number of cycles. And their definitions are quite similar. While one is the time taken to cover a cycle, the other is the distance traveled in one cycle. So the time of one cycle is a period, the distance of one cycle is a wavelength. And if you have to get the wavelength, you must just divide the distance that you have been given by the number of cycles that that wave has covered in that distance. If, for example, for this pattern that is shown on the board, this is 10 meters, then it means I've been given the distance from this 0 point to this place as 10. I now need to count the number of cycles that make up that 10. This is half, 1, that's a full cycle, 1.5, 2, that's 2 cycles, 2.5. So I have 2.5. If you divide 10 by 2.5, you are going to get 4 meters. If this is in meters, then that is the wavelength. The wavelength is equal to 4 meters. If I just change this to time, if this had been time, and of course the unit of time is not meters, it's seconds, and I can ask you to find the period. This is exactly the way you are going to find the period. Get the time, which is 10 seconds, and divide it by the number of cycles that you are given on the board, which is 2.5. If we do that, you will discover that your answer will also be 4 seconds. So that's why I said we determine wavelength the way we determine the period. The only difference is just that the notation on the axis must be different. While one is distance, the other one must be time. So now, there are other definitions that people can also give you that also means the same thing as defining wavelength or period. Remember that I said that a period or a wavelength is the distance covered by the wave in one cycle. The distance covered by the wave in one cycle. Now, I may not use the word cycle directly. I can now give you things that also ultimately translate into cycle. For example, this is a crest. If this were to be a transverse wave, this is a crest, this is a trough, this is a trough, this is a crest. By the time you look at it, from what we discussed under points that are in phase, I hope you will know that one crest and the next crest are in phase with each other. Why? They are in the same direction. In fact, the crest is the maximum point. There's no movement at the crest. There's no movement at the trough. And the two of them have the same displacement. They have the same direction, no direction, and they have the same displacement. So two successive crests also make up a cycle. Because I told you that 2 points that are in phase, 2 successive points that are in phase makes a cycle. 2 successive crests that are also in phase makes a cycle. 2 successive troughs that are in phase makes a cycle. If we are talking about the other type of wave, that's longitudinal. 2 successive compressions also make a cycle. 2 successive rarefactions also make a cycle because there are no crest and trough on longitudinal wave. What we have on longitudinal wave are compressions and rarefaction. So when you have a compression and the next compression, the distance between them must be their wavelength. The rarefaction and the next rarefaction, the distance between them must be the wave's wavelength. So a crest and the next crest, the distance between them must be a wavelength. The trough and the trough, the distance between them must be a wavelength also. So when we do that, so I can now tell you that a cycle has so many definitions. So whatever depends on the cycle can also be referred to as in so many different ways. I can define a wavelength as thus. A wavelength is the distance traveled by the wave in one cycle. A wavelength is the distance traveled by the wave from a crest to another crest. It's the distance traveled by the wave when going from one crest to another. It's the distance between a trough and the next trough. It's the distance between 2 successive rarefactions. It's the distance between 2 successive compressions. It's the distance between 2 successive points that are in phase. Any of those things means the same thing as wavelength. Wavelength is the distance covered by the wave in one cycle. It is the distance between 2 successive crests, the distance between a crest and the next crest, the distance between a trough and the next trough, is the distance between a compression and the next compression, is the distance between a rarefaction and the next rarefaction, is the distance between 2 successive points that are in phase. Similarly, we can define the period as thus too. The period is the time taken by the wave to cover a cycle. It is also the time taken by the wave to go from one crest to the next crest. It's the time taken by the wave to go from a compression to the next compression. The time taken by the wave to go from a trough to the next trough. The time taken by the wave to travel between 2 points that are in phase. The time taken by the wave to go from one rarefaction to the next rarefaction. There are instances you will be expecting period or wavelengths, and they will give them to you in any of this form. You must be able to know that what you are giving is still the wavelength. Now we talk about the wave speed. Speed is distance over time. So the speed of a wave is the distance traveled by the wave all over the time that it took the wave to travel that distance. So the speed is represented with small letter v, just as speed in motion, v. The distance I told you earlier is represented by the letter x. The time is represented with the letter t. So this is the formula for finding the speed of an object that is traveling, of a wave, the speed of a wave. Now there are instances where we can invert this formula to give us another formula. If we are talking about a cycle, I hope you know that for a cycle, the distance becomes the wavelength, because the wavelength is the distance traveled by the wave in one cycle. In that case, the time becomes the period. Because the period is the time taken by the wave to travel one cycle. So therefore, I can re-express my speed as wavelength all over the period. I can now also say that this is wavelength times 1 all over t. If I bring this t out, you know the t is a denominator. If I want to bring it out of this lambda, I'll put 1 all over lambda. If that is the case, I can say that that is wavelength multiplied by 1 all over t. The meaning of 1 all over t is f. So therefore, I can say that my velocity is equal to wavelength multiplied by f, or more appropriately referred to as f lambda. This is the most important equation under wave. V, the velocity of the wave, is equal to the frequency multiplied by the wavelength. If I know the frequency and the wavelength, I can get the velocity. If I know the wavelength and the period, I can also get the velocity. Sometimes I will not be giving any of the two. I'll just be giving a distance and a time value. That can also be taken as my velocity. I can use that to calculate my velocity. Please take note of all of this. Wavelength is a length quantity. It is also measured in meters or smaller or bigger units, meters, kilometers, depending on the type of wave that we have. Now, we have seen that a wave can be described with any of these quantities. I told you that we can plot the displacement of the particle with the time and the distance on this other side, either the distance or the time on this other axis, while the displacement is on the other axis, the displacement is on the y-axis. There is a formula that is regarded as general wave equation that can be used to connect between the displacement and the distance, such that if you give me the distance, if I need the displacement of a point, and I have been given the distance traveled by the wave to get to that point, and the time that it took the wave to get to that point, of course, the two of them will have to be determined on two different axes. If you give me the distance and the time, I can slot them into that equation to get the displacement of this point. The equation is called the general wave equation, and it can be simply expressed as y is equal to a sine omega t plus or minus kx. That is our general wave equation. Y is equal to a sine omega t plus or minus kx. That's it is called the general wave equation, and we can use it to determine the displacement if we are given the time and the x values, that is the distance values. But of course, before we do that, we need to know the other terms that I've used. This is the displacement, as I've said earlier. This is the time. This is the distance. Now, the K omega A, we have talked about A. A is the maximum displacement. The maximum displacement of that wave. It is a constant. There are two other constants that we are using. Omega is a constant. I'm going to define it now. K is also a constant. A can be read directly from the graph, or it is given. Omega is called the angular frequency or the angular velocity of the wave. The angular frequency or the angular velocity of the wave. It has the formula, we can get it from 2 pi f 2 pi, then f. 2 pi, they are constant. Pi is your 22/7. F is the frequency, and I've already explained how to get the frequency. That means if you know the frequency, you can find the angular frequency from that expression. Now, K is called the wave number. We determine it from 2 pi all over lambda. 2 pi, then lambda is the wavelength of the wave in meters. So K is the wave number, and it is expressed as thus. So I can, if I decide to put all of this into that equation, I will have y is equal to A sine, open bracket, 2 pi f, that's what I'm substituting for omega t, plus or minus k. K is 2 pi f, 2 pi all over lambda multiplied by the x. So this is another form of it. Of course, this is a very simple form of it. Once you know your omega and k, you can just now substitute for them later. But if you want to substitute for them in that equation, you can have something like that. If I factorize in some other forms, so you can factorize 2 pi out of that bracket, then I will have y is equal to A sine 2 pi, open bracket, ft plus or minus x all over lambda. And there are still other forms. There are still other forms that we can have. I can factorize f out of this bracket. If I factorize f out of the bracket, we know exactly what it means. You can see me using a positive and negative sign. It becomes positive. You can have positive in the bracket. You can also have negative. Positive is just referring. It becomes positive only when the wave is moving in the left direction of the origin, but if that is in the negative x-axis. If it is moving in the negative x-axis, we use a positive sign. If it is moving in the positive x-axis, we use the negative sign. So the sign that I use here is the direct opposite of the sign or the direction that the object is traveling along the x-axis. Another thing that I need to also talk about is you can also substitute for this sign. It's not compulsory that you have sign all the time. In fact, you can also have cos, because both cos and sine are equations that will give us sinusoidal form. That is, forms that will express the wave in this manner. The only difference is y sine can be used to express a wave that is starting from the origin. Cosine can be used to express a wave that is not starting from the origin. And in both cases, every other one of your quantity remains the same. Whether it is represented like this or like this, your amplitude remains the same, your wavelength remains the same, your frequency remains the same, your period value remains the same. If you have your sine replaced by cos, it is still a standard wave equation. The only thing that you cannot use of the three trigonometric functions that you know is tan. You cannot replace this with tan, because tan will not give you a sinusoidal form like this. So with that, we have come to the end of the mathematical representation of a wave. We'll try to take one or two examples to properly understand what we have talked about. Now, we have a question here. We are told that a wave is represented by the equation y is equal to, a wave is represented by the equation y is equal to 0.20 sine, open bracket, 0.4 pi, open bracket, x minus 60t, close bracket, then close bigger bracket. So the question is, where x and y are in centimeters, x is in centimeters, y is also in centimeters. It is possible that the two of them are in the same unit. It is also possible that they are in different units because what they want to give us are completely different from each other. And t is in seconds. T is in seconds. T is in seconds. The question wants us to find the question wants us to find the amplitude. And two, the question wants us to find the velocity of the wave. The velocity of the wave. How do we solve this question? What we'll do, quite simply, is that we'll try to break the bracket. We'll break the inner bracket. We'll break it so that we have an equation that looks very similar to our general wave equation. We'll break the bracket by using this to multiply this and by using this to multiply it. If we do that, we will have y is equal to 0.20 sine 0.4 pi x minus, if we multiply 0.4 pi by 60, 0.4 times 60 is 24 pi t. When you have this, you will now write your general wave equation directly under it. You write your wave equation directly under it. Our general wave equation is y is equal to a sine, what I just gave you now, open bracket, omega t plus or minus kx. So if you have that, what you will need to do is just to compare the terms. Compare the terms. If I do that, clearly my A is equal to 0.2. My A, which is the amplitude, remember that I said A is the amplitude and there's a 1 in front of the sign. Your A is the amplitude and the amplitude will be 0.2 centimeters because A will have the same unit with your Y, and we have been told that our Y is in centimeters. So sometimes the equation will look so big, but all you just need to do, all that you are required to do is to just pick out your answer and get it. For example, the amplitude is as simple as just picking it out from that equation. There's no addition, subtraction, or multiplication that you have to do. Now we want to get the velocity. Before we get the velocity, I want us to look at similar terms again. The term that has a t here, there will always be a term that has a t, must be equal to the term that has a t here. That means the whole of this term must be the same thing as the whole of this. The term that has my x here must also be the same thing as the term that has my x here. So that means the whole of this term must also be equal to this. If that is the case, then I can now write them out. I'll have kx is equal to 0.4 pi x. Of course, x can cancel out x. And remember that I said that your k means the wave number. The wave number can be expressed as 2 pi over lambda is equal to 0.4 pi. If we divide both sides by pi, we'll cancel out this, and we can make lambda the subject of the formula. When we do that, lambda becomes, if we cross multiply, 0.4 lambda is equal to 2, while lambda becomes 2 divided by 0.4. If we divide 2 by 0.4, we'll have 5 in centimeters, because it must also have the same unit as your x. Now, we write the other part of the equation. Omega t must be equal to 24 pi t. So the item that has t in the given equation must be equal to the item that has t in your own standard equation. The item that has x in your equation must be equal to the item that has x in the given equation. So those are the things that will guide you and guide your ability to be able to solve questions like this. So we can cancel out t and t. Our omega should be 2 pi f must be equal to 24 pi. So if we cancel out the pi, f ultimately becomes 24 divided by 2. And 24 divided by 2 is 12 hertz. If that is the case, we can now determine the velocity. The velocity of this wave, mind you, is f lambda. That's the formula for finding the velocity. We said that, we gave this formula earlier. If we know the frequency and we know the period, we know the frequency and the wavelength, we can find the velocity. The velocity ultimately becomes 12 multiplied by lambda is 5 centimeters. Mind you, this is in art is per second, and this is in centimeters. If you multiply them, we should have 60 centimeters per second. Or if you are not so comfortable with solving in centimeters per second, you can also change your centimeter value to meters by dividing by 100. So it will be 12 times 0.05. If you multiply that, you should have 0.6 meters per second. And that leads us to the end of the question. We'll take more questions. Another question that we would like to look at is this. Water waves are generated by dropping stones at regular intervals at a point in a pool of water. The first crest reaches another point 8 meters away in 4 seconds. The first crest reaches another point 8 meters away in 4 seconds. If the distance between two successive crests is 0.5 meters, the frequency of the wave is dash. We are told that a crest was generated and that crest reaches another point. We don't know if the other point is also a crest, but the crest reaches another point 8 meters away in 4 seconds. If you are not sure, if they give you distance and you are not sure of that distance, just call it distance. 8 meters. Luckily, we are also given the time that it took the crest to get to that point 8 meters away. It got to a point that is 8 meters away in a time of 4 seconds. So I'll just represent that with my time too, because I don't know if that is a period. It was a crest that was generated, and that crest got to another point which is 8 meters away from it in a time of 4 seconds. If you are given the distance and the time that it took you to travel that distance, you can just represent them as x and t. Now, this is where the question becomes interesting. They said, if the distance between two successive crests is 0.5 meters, the distance between two successive crests is the wavelength. I was telling you earlier that it is possible for them to give you wavelength without directly using the standard definition of wavelength that you know. Wavelength is the distance traveled by the wave in one cycle. Here, they have not referred to that distance as one cycle. They have referred to that distance as the distance between two successive crests. So it is necessary for you to review what we have said earlier, where I mentioned that wavelength can be referred to with so many other parameters. It could be the distance between successive crests, distance between successive troughs, distance between 2 points that are in phase, distance between two successive points that are in phase, distance between two successive compression, distance between two successive refractions. Please get all of these things noted, because these are things that the questions can give to you. And if you don't know them that way, they will give you most of this quantity and you will not know that you have actually been given. For example, if I don't know that wavelength can also be expressed as the distance between successive crests, I'll be looking for the wavelength in that question and I will not find it. Now we'll continue. The question now is that we should find the frequency of the wave. The frequency of the wave. They want me to find the frequency of the wave. The very first thing I want you to know is anytime you are given the distance and time for that distance, you can evaluate the velocity. I said it earlier. I want you to review our notes to see where we have used this. The velocity is the distance all over time that it took to travel that distance. The distance given in this case is 8 meters, and the time that it will take you to travel that distance is 4 seconds. The velocity, therefore, will be 2 meters per second. If the velocity is 2 meters per second, then I can find the frequency, the ones that have been given the wavelength. Mind you, we know that the velocity is frequency times wavelength. So the frequency must become the wavelength, the velocity divided by wavelength. And the velocity is 2, the wavelength is 0.5. If we divide that, we should have 4 hertz. And that is all about that. So that is another question that we've been able to take. And there's still more. There are so many ways by which you can be given a wave problem. We are given this graph. Yes. We are giving points on the graph. We are giving this to be point A, point B, point A, point B, and point C. Also giving point F, G, H, this is E, this is H, D, K, point D, point K, L, M, L, M, N. This is I, and this is J. A, B, C, D, E, F, G, H, I, J, K, I, J, K. We are asked to find, for the first question, we are asked to find which of the following distances is not equal to a wavelength of the wave. C, J, B, H. BH, which of the following distance is not equal to a wavelength? BH is equal to a wavelength. B to H is a wavelength. Why? Because both of them are in phase. They are the same displacement. And being at the same displacement, they also have the same direction. Points from here to here are moving down, while points along this direction are also moving down. So they have the same direction. And we have DK. Point D and point K are not in phase. Yes, why the two of them have the same direction? Why the two of them have the same displacement? They don't have the same direction. Point from here, points along this direction are going up, while points along this direction are moving down. And for 2 points to be in phase, they must be moving in the same direction. So that is the answer. D to K are not in phase. Now, what is the phase difference between point A and J? What is the phase difference between point A and J? How do we find the phase difference? If 2 points are in phase, their phase difference is equal to 0. If 2 points are in phase, their phase difference must be equal to 0. Whether they are successive or they are not successive, their phase difference will be equal to 0. For example, A to B, A to G, because they are in phase, both of them are crests, their phase difference is equal to 0. G to M, because they are in phase, their phase difference will also be equal to 0. Now, if 2 points are not in phase, then there will be a difference in their phase. There will be a difference in their phase. If those points are far apart, we must look for a point in the neighborhood of the other point that is in phase with the first point. If A to B are not in phase and they are far apart, we will look for a point in the neighborhood of B that is in phase with A, and we will look for the difference between the phase of C and B. For example, the question wants us to find the phase difference between A and J. A, this is point A, and this is point J. A and J are obviously not in phase, so they will have a phase difference. What will be their phase difference? I must look for a point that is in the neighborhood of J that is in phase with G. With A, I want to find the phase difference between A and J. I will look for a point around J that is in phase with A. And the closest point to J that is in phase with A is G. The next point that is in phase with it is M, and M has already passed it. I'll look for a point to it, not a point beyond it. A point before it that is within its neighborhood, that is closest to it, that is in phase with the first point. I want to find the phase difference between A and J. I'm going over it again. The very first thing I'm going to do is, if they are far apart, as in this case, I will look for a point that is around J, just before J. A point just before J that is in phase with A, and that point is point G. So when I get to point G, I will now find the phase difference between G and J. The reason for that is there's a maximum value that you must not get for phase difference. There's a maximum value that you must not go beyond. Anytime you are getting the phase difference. Phase difference is expressed in angle, and you are not expected to get a value that is more than 360 degrees, or if you express that in radian, 2 pi. There are two forms that we can use to express our angle. We can use degrees, that's the total angle at a point, 360, and we're allowed to also use radian. We're allowed to also use radian. In radian, 360 degrees is exactly equal to 2 pi. So you are not anytime you are finding phase difference, you are not expected to find any angle that is beyond this value. If it is beyond 360, you can subtract 360 from it until you get a value that is less than 360. If it is more than 2 pi, you are required to subtract 2 pi from it until you get a value that is less than 2 pi. So one thing that will ensure that you don't get a value that is more than what you should get is to pick a point that is closest to your J and try to find the phase difference to that point. So if I want to do that, what I will just do now is to count the number of cycles that I have between the given point and between the points that I've now found and the given point. So I'll find the number of cycles between G and J. Normally, I should have found the number of cycles between A and J, because that's what the question requires of me. But in that case, I will be getting something that is more than the allowable limit for this answer. So that's why I'm picking a point that is closest to J. So I will now look for the number of cycles between G and J. I expect you to know that this is half and this is a quarter, based on what I've mentioned earlier. So I have half. The number of cycles that I have between J and G is half and a quarter. So half and a quarter, if you put that in fraction, is 3/4. So I have 3/4 cycle between G and J. What I need to do now is to multiply 3/4 with my 2 pi, because a cycle is 360. So 3/4 of a cycle will be 3 all over 4 times 2 pi. If I do that, I will have 2 here 1, 2 here 2. And the answer should just be 3 pi all over 2. That is my answer in radian. If the option were put in degrees, I will do 3 all over 4 times 360. 3 all over 4 times 360. 4 here 1, 4 here 90. 3 times 90 should give me 270 degrees in degrees. So the phase difference between A and J is also the phase difference between G and J. And I've been able to find that as given on the board. Now we look at the properties of a wave. Things that a wave must possess before we can call it a wave. The properties of a wave are the ones I'm listing on the board now. The first property of a wave is all wave can be reflection. All wave can undergo refraction, and all waves can undergo diffraction. All waves can also undergo interference. And the last one, some waves can undergo polarization. Now, while property 1, 2, 3 to 4 while property 1 to 4 applies to all waves, polarization applies only to a transverse wave. Only transverse waves can be polarized. So most of the time we get this question that what is the exclusive property of a transverse wave? The answer is polarization. Exclusive means something that it is only you that have it. It is only that thing that has it. Polarization is the exclusive property of a transverse. Only transverse waves can be polarized. Any wave that is not transverse, particularly longitudinal wave, cannot be polarized. So sound cannot be polarized because it is a longitudinal wave. But all other waves, whether longitudinal, transverse, can undergo reflection, refraction, diffraction, and interference. So we do that. Now, a reflection is the ability of a wave to return back to its incident medium. We'll just look at them briefly because these are properties that we are still going to discuss in details in the course of our lessons. Now, reflection is the ability of a wave to return back to its incident medium, to return to its incident medium. When you say a wave is reflected, it means the wave is sent back to the medium where it came from. If you have a wave moving in a particular direction and it hits a surface that can reflect it, and the surface can now be, the wave can be returned back to its incident medium. Reflection is a property of all waves. All waves can be reflected. And it is just that the material that is required to reflect all waves differs. For example, light. Light is usually reflected by a very smooth and hard surface. Sound is usually reflected by a rigid and hard surface. And most other waves are reflected by hard surfaces. But all waves can be reflected. If you have water waves, if you have wave on a rope, I hope you know that when you generate wave on a rope by agitating one end, by the time it gets to the other end, we expect it to hit the wall, and the wall will return it back to where it came from. That is your hand. So when you have something like this, if you continuously generate the wave, despite the fact that when they get to the other end, they will come back, you will set up a wave that looks like this. And we have already discussed this before. This is a stationary wave. So one way by which you can generate a stationary wave, remember we said that for a stationary wave, there must be two waves, and the two of them must be traveling in opposite direction. One way by which you can generate a stationary wave is for the wave to move in a direction, and you have another wave, and you have this reflected form that is moving in the opposite direction. If the two of them are combined, that means being generated continuously at the same time. Then we have a wave that looks like this, very much like this. So that is an example of a stationary wave. All waves can be reflected. When sound is reflected, it produces what is called echo. So if you speak to a wall and you're able to hear what you said back, that means the sound has been reflected. Reflected sound is called echo. When there is multiple reflection, that is when we call it reverberation. We are going to see that when we get to sound. So all waves can be reflected. There are laws that govern reflection. We are going to see it properly when we get to light. Refraction of a wave. Refraction is the change in the speed and the direction of a wave as it travels between medias of different densities. When a wave travels from one medium to another, its pattern, its speed, its direction will change. In fact, even its wavelength will change. So the change in the wavelength, the change in the speed, and the change in the direction of a wave as it travels between media of different density is called densities. It's called refraction. A very good example, if we have light coming to a surface, all the while the light was traveling in air. When it gets to a glass surface, let's assume that this is glass. When it gets to glass, it is not going to continue in that same form that it was traveling. Its direction will bend a little. If its direction bends, we also believe that the speed in glass will not be the same as the speed in air. The speed in air is about 300 million meters per second, but the speed in glass will be a little bit lower than that because its direction, its path will be greatly affected. So this change in path, this change in the direction as the wave is trying to pass through different medias of different density will be called refraction. All wave can also be refracted. Sound can be refracted, light can be refracted, the wave on a rope can be refracted. If it is possible for you to allow the wave to move into another segment of the rope, that is not the same with the rope that you were using earlier. Water wave can be refracted. For example, if you allow the wave, let's say we have a segment of water, and just after that we have patch of oil after it. When the wave is about to cross the interface between water and oil, the shape, the pattern of the wave, or the speed of it, the wavelength, the wavelength and the speed will also change. In fact, refraction changes almost everything about a wave. The only property that is not affected anytime a wave is refracted is its frequency. When a wave is refracted, the frequency remains unchanged. The speed will change, the direction will change, and the wavelength will also change. Diffraction. Diffraction is the bending of a wave around an obstacle. Is the ability of a wave to bend around an obstacle. The ability of a wave to bend around an obstacle. If, for example, we have a wave, let's say we have a wave that is set up by dropping a straight object, like a plank, on the surface of water. If we now have straight waveform, then just around the path of that wave, you now place an obstacle that the wave will have to pass through. It is possible that in passing through that obstacle, the pattern of the wave will change. The pattern of the wave changes. When that takes place, we say that the wave has been diffracted. So the change in the pattern of a wave, or the ability of a wave to pass through tight opening that is placed, or narrow opening that is placed in their path, is what is called diffraction. So diffraction does not always occur, or diffraction does not always take a full form like the one I've drawn. Here you will see that straight waveform have been completely transformed into circular form because they are trying to force their way through that opening. So it does not always happen like this. It will only occur if the size of the opening, let me call it A, is less than or within the same dimension as the wavelength. Let me call this the wavelength. If this is the wavelength, if the opening is less than the wavelength, then we will have a full diffraction pattern as the one I have drawn. If the opening is a little bit larger, than what you have, you only have a slight diffraction pattern at the edges. Much of the wave will remain the same. You have a slight diffraction pattern at the edges. Much of the wave will remain the same because here the size of the opening is if the opening is less than the wavelength, if the opening is larger than the wavelength, that is when we expect that there won't be much of diffraction. You just have slight curves around the edge of the wave. So the ability of a wave to force itself or to travel through narrow opening that is placed in its path is called diffraction. Then we'll move on to interference. Interference is an effect that is produced when two waves of equal frequency wavelength traveling in the same direction are superposed. Interference is an effect that is produced when two waves of same frequency, wavelength, and amplitude traveling in the same direction are superposed. That looks very much like what I gave earlier for the definition of polarization, but it is not the same with the definition of polarization. In polarization, the two waves must be traveling in opposite direction. In interference, the two waves must be traveling in the same direction. So interference is an effect that is produced when two waves of equal frequency, wavelength, and amplitude, but traveling in the same direction are superposed. If I have a wave and another wave very similar to it, traveling in the same direction, if I decide to superpose or combine the two of them, then the effect that I will have will be called interference. And there are two types of interference. I can have what is called constructive interference. I can also have what is called destructive interference. When you combine the wave such that like parts, like a crest is falling on another crest, a trough is falling on a trough, a crest is falling on a crest, a trough is falling on a trough, another crest is falling on a crest, and a trough is falling on a trough, then we will have a much larger disturbance or wave. We'll have a much larger disturbance. It's like the two waves will come together to help each other. So we have a larger disturbance such that the amplitude of this one will be twice the amplitude of the two waves. If they are equal, the amplitude of what you are going to get, the resulting wave, will be twice that of each of the individual waves that you have merged. So when this happens, we'll call this one a constructive interference. The two waves have combined constructively. That is why you are forming a larger wave. But in a situation where you have a wave and another still of the same frequency, but this time they are combining such that a crest is falling on a trough is falling on a crest, another crest is falling on a trough is falling on a crest is falling on a trough. If they combine as such, it looks as if the crest here will cancel out the trough because the two of them are in opposite, the two of them are opposite in pattern. So they will cancel out. They are not like parts. The trough here too will cancel out the crest. The crest here will cancel out the trough. So ultimately you have a no wave or a wave that is almost not visible at all. Then in that case, it means the two of them have combined, is combined destructively. So we'll say that this is destructive interference. So interference can be constructive and interference can also be destructive. Then we'll look at the last property of a wave, which is polarization. Like I said, polarization is an effect. Polarization is a property that is exclusive to only transverse wave. It is only transverse wave that can be polarized. All other waves cannot be polarized, particularly light. Light is a transverse wave, it can be polarized. Water is a transverse wave, it can be polarized. Wave on a rope is a transverse wave and it can be polarized. Polarization is the effect of producing a wave whose vibration is in only one plane. Polarization is an effect of producing an effect that allows the production of a wave in only one plane. If we have a wave on a rope and I choose to agitate it vertically upward and downward, then we will have a wave that will vibrate in only the vertical plane. Now imagine that as I am doing that, I am also vibrating it sideways. Then I will have a wave whose vibration is also in the horizontal plane. As I'm doing that too, let us imagine that I'm also vibrating it in an inclined form. I will have a wave whose vibration will be in an inclined form. It's so easy to have that. When you wave it vertically, you wave it horizontally inclined, then you have a wave that will, the kind of wave that you are going to produce will be in different planes, vertical, horizontal, inclined. So when you have that, we'll say that you're having an unpolarized wave. An unpolarized wave. If you need to represent an unpolarized wave, you don't need to draw something as rough as what I have on the board. All you just need to do is draw a plane and show the various directions in which you are trying to cause the vibration. If you do this, it means you are producing a wave in the vertical plane. If you do this, you are producing one in the horizontal plane. If you do this, you are producing one in the inclined plane. If you do this, you are producing another one in another inclined plane. So once you just draw a straight line, I understand the type of wave that you are going to try to get. It means generally you are going to have a wave that is in 1, 2, 3, 4 planes. Now, that is an unpolarized wave. If I place a polarizer along the path of the wave, a polarizer will allow only the wave whose vibration is in the plane of the opening of that polarizer to pass through. Only the one that is in the vertical plane will pass through. Every other one, by the time they get to the opening, they will be consumed by that opening. So it is only the one that is vibrating along the axis of the opening of that polarizer that will be allowed to pass through. And now we call this one a plane polarized wave. A plane polarized wave, particularly if it is light, it becomes a plane polarized light, and its vibration will be in only one plane. So the process of changing an unpolarized light to a plane polarized light is what is called polarization. And there are so many methods by which we can use to polarize, particularly light. Light can be polarized by what is called, by allowing it to pass through polarizers. And examples of polarizers are tourmaline crystals, quartz. You can get more of that from your textbook. It can also be polarized by reflection. Generally, if you allow unpolarized light to hit a smooth glass surface, unpolarized light to hit a smooth glass surface at an angle of incidence of 57, then the reflected wave, the reflected light will be plane polarized. There are still so many examples that we can use to polarize waves and all other types of waves. So with that, we have come to the end of wave. I hope you've had an interesting time. Please join us again for the treatment of another topic in physics. Thank you very much.